So if you recall, what I talked about last time was the second attempt at doing the same thing. So 2 sessions ago, we integrated something. And integrating something is taking an expression with no unknown functions in it and integrating it over the mesh and getting a number. So what we did last time was we did the right-hand side, and the right-hand side has a test function in it. So it's got one unknown function in it. So we integrated something with one unknown function in it over the mesh, and we got a vector. And on the left-hand side of your finite element problem, you have 2 unknown functions because you have a test function and a trial function. So you integrate something with 2 unknown functions over the mesh, and you get a matrix. Because a matrix is something which will take in 2 vectors of coefficients and give you a number back. So that's what we're doing, and the process is actually really the same as what we've seen so far. The other little complication that we ducked up to this point was, up to this point, every time a finite element function occurred in an integrand, it was the function itself. And at least for nice, well-behaved functions in H1, so the spaces we've been looking at, the value of the function on the reference element is the same as the value of the function in physical space. Right? It's only where you are which changes, your value doesn't change. If you take a gradient, that's not true. So when I write grad u in the PDE, that means the gradient in physical space. That is to say, it's d phi, or the function, but once I expand the function into a finite element space, that's just d phi d little x for all the components of little x. But when I take a gradient of a basis function on the reference cell, I'm taking d big phi d big x, right? On the reference cell, I have no concept of what the directions are in physical space. I can only see the reference cell. I've only got my little local x and my local y. The only thing I can possibly take derivatives with respect to is the local coordinate space. So that means that when we take a derivative, we need to not just change coordinates into local space for where we are, which is something we've already worked out. We have to then take the value of the derivative, and change coordinates to get a derivative back in the physical space. So fortunately, you all know how to do vector calculus, and so this isn't actually news. So here is my, so if I write out my, so that's what a gradient operator looks like, right? So I have a basis function, a global basis function, and it's one of the global basis functions on the current element. That's what it means when I subscript it with MCI. And I'm taking its derivative in physical space. So that's equal to the derivative of the local basis function at the corresponding local point with respect to physical space. So halfway there. But now I've got a big X on the top and a little x on the bottom. And as previously mentioned, I don't know how to do that. So I have to do chain rule. And so what I get out of that is that this thing again is equal to the gradient I do know how to do. So this is the gradient of the basis functions with respect to the local coordinates. And if I knew the points I was evaluating this at, so for example, if I'm doing it at quadrature points, then that bit is what tabulate does. If you call tabulate pass grad equals true, it gives you this guy, right? It's tabulate returns a 3 tensor. One of the tensors, the first one is the set of points, the second one is the set of basis functions, and the third one is the direction that you're taking the gradient in. Brilliant. And chain rule says that what I get here is dx beta d little x alpha. So this is the Jacobian of the transformation. It's the gradient of the local space with respect to the global space, which is very, very nearly what we did previously. And so if I write this in vector calculus notation, so using nabla for grad and subscripting it by the coordinate system so I can know which nabla is the local one and which nabla is the global one, then all that is the global gradient is equal to the local gradient multiplied by the inverse transpose of the Jacobian. So minus t, if you haven't bumped into it before, is a conventional notation for take the inverse and take the transpose, or vice versa, because they commute. And that J is the cell Jacobian that we already worked out how to do. Right? The cell Jacobian is d little x, d big X. This one is d big X, d little x, and it just so works out that if you have a Jacobian and you dot product it onto the right-hand side, you end up contracting out over what's on the bottom of the Jacobian, and that's not what we want. We need to contract out over what's on the top, and so the way you deal with that is you transpose it, and then dot product does what you want it to. So that's the change of coordinates. So every time you get a gradient turning up in a integrand, we need to transform it into a local coordinate operation like that.